Hi, my name is John Wren, and I'm a PhD student at Brown University presenting on how we use relational problems to teach property-based testing. In a relatively short period of time, property-based testing, or PBT for short, has gone from research idea to industry-accepted practice. With PBT, we can do things like test every floating point number and handle the uncertainty inherent in virtually any large specification. But, as a community, we've done an awful job of teaching it. PBT is a sophisticated technique that shines on sophisticated problems and is supported by sophisticated frameworks. Teaching all of this complexity at once is daunting, and simple examples like reversing a list twice fail to actually motivate people to learn any of it. But we contend that you don't need sophisticated problems to actually motivate PBT, and you don't need sophisticated languages or frameworks. To motivate PBT, all you need are relational problems, problems for which a single input might correspond to multiple valid outputs. These problems are pervasive in computing education. For instance, consider the procedure sort by age, that's specified to consume a list of people, each with a name and an age, and produce that list sorted in ascending order by age. For particular inputs, like this one here, this procedure might seem like a function. On this input, with ash age 2 and cal age 1, the spec admits only one valid output, cal, then ash. But for any input that has two people with the same age, the output is uncertain. On this input, an implementation might either order Eve before Ada, or Ada before Eve. Sort by age isn't a function, it's a relation. And property-based testing, in which we construct predicates that relate inputs to their valid outputs, gives us a tool for testing such specifications. Relational problems are pervasive in computing education. Just as a sorting procedure can be unstable, a graph might admit multiple minimum spanning trees or have multiple shortest paths between two vertices. In the case of seam carving, an image might have multiple seams with equal energies. Most college-level students will probably be asked to implement at least one of these problems, but they are rarely taught the property-based techniques that they will need for testing. In our courses, we teach a simple recipe for property-based testing. When you need to test a procedure whose exact output is uncertain, first, you implement a predicate, isValid, that consumes a sample input and a corresponding output, and produces true if that output is valid for the input. Now, when you're testing, you can use isValid to check whether the behavior of the procedure under test conforms to your spec. Simply construct an input, pass that input to the procedure under test, and assert isValid produces true for that input-output combo. Next, implement a procedure called generateInput that randomly generates a sample input of a given size for the procedure under test. Now, instead of writing our testing inputs out manually, we can compose these two utilities to get a general gadget for testing any relational procedure. And if we take this code, and we run it in a loop for different input sizes, we have ourselves a fully fledged testing oracle, a predicate that consumes the procedure under test and produces true if it's probably correct. At Brown University, we teach this recipe in two different courses, with very different populations and subject matter for very different reasons. The first is an accelerated introduction to computer science, where mostly first-year students complete programming projects focused on data structures and algorithms using a functional programming language. The second class, Logic for Systems, has upper-level students use modeling languages like Alloy to encode specifications. In the accelerated intro, we teach this recipe so that students can correctly and thoroughly test the many relational problems that they'll face in the course. In Logic for Systems, this recipe is taught to ease students into thinking about the logical properties of specifications in a language they're already comfortable in, like Python or Java. Most of these students aren't coming from the accelerated intro, so this is their first contact with PBT. In both classes, the recipe is introduced through an assignment where students focus specifically on PBT. In a PBT-focused assignment, students are given a specification for a procedure's behavior. However, instead of implementing that procedure, they instead implement a testing oracle for it. For their deliverable, they need to implement isValid, generateInput, and an oracle procedure that composes those two together. In the accelerated introduction, there are actually two assignments in this form, the first of which is called Sortacle. Sortacle Specification describes a procedure that consumes a list of people, each having a name and an age, and produces that list sorted in ascending order by age. Since this is a relation from list person to list person, our isValid is going to be a function that consumes a pair of list persons, representing the input and output, and produces a Boolean. To implement isValid correctly, students must reflect on what properties relate an arbitrary input to its valid outputs. In the case of sortedness, we might decompose this as a conjunction of three properties: that the input and output list have the same size, that they contain the same elements, and that the output list is correctly sorted. Doing this well is a skill that isn't specifically taught to most programmers, so it's worth investigating how students fare at it. Namely, are students able to execute the basic gist of this scaffold? If so, what properties do they have the most trouble enforcing? And do they actually respect the relational nature of the problem? We can evaluate each of these questions by writing our own test suite that we run against student implementations of isValid. To answer whether students are even able to execute the basic gist of this scaffold, we construct a test suite called Functional that will accept even minimally correct implementations of isValid. This test suite has two kinds of tests. Tests where isValid produces true for input-output pairs where output is the only result admitted by input, and false for completely unrelated input-output pairs. We call these first set of tests where isValid produces true positive test. These are simple test cases where there's only one possible output for each input. A student doesn't actually need to do property-based testing to pass these. They could simply sort the input and check that the result matches the given output. But a stub implementation of isValid that always produces true would also pass these tests. So we also need negative tests, tests where the expected output is false. But what input-output combos should we use here? To answer that, we think about our properties of sortedness. A totally correct implementation of isValid needs to enforce all of these properties perfectly. That the input and output are the same size, that they contain the same elements, and that the output is ordered. But a minimally correct implementation ought to enforce at least one of these. So, for these tests, we pick input-output combos where none of these properties are satisfied. The input and output will have different lengths, they'll have different elements, and the output won't be ordered. Like this. Together, these simple positive and negative tests let us identify the isValids that at least basically work. The isValids that accept simple, valid input-output combos and that reject the catastrophically invalid input-output combos. And, running this test suite against our student submissions, we find that, yes, students were able to execute the basic gist of the assignment. Of the 205 Sortacle submissions produced between 2017 and 2019, only 3 failed the functional test suite. Next, we can use this evaluation to serve as a baseline for answering our other questions. Did students actually respect the relational nature of the problem? In which properties did they have the most difficulty enforcing? Sort by age has inputs for which there is more than one acceptable output, like this earlier example where Ada and Eve have the same age. To check whether students respect this relationality in their isValids, as opposed to just sorting the input list, we construct another test suite called Relational. The Relational suite has tests involving an input that has multiple valid outputs and checks that every possible output is considered valid. The number of isValids that didn't respect the relationality of this problem is the count of those which were accepted by the functional suite but rejected by the relational suite. In our case, only one student across 3 years didn't respect the relationality of this problem. We use a similar technique to answer our final question. Which properties did students have the most trouble enforcing? For this, we'll make a distinct test suite for each subproperty that checks whether that specific subproperty is being enforced. These suites do that by supplying input-output combos where every property is satisfied except one. For instance, the enforced ordered suite doesn't care whether an isValid enforces that the input and output are the same size. It doesn't care whether they have the same elements, but it will reject any isValid that doesn't produce false for an output that isn't ordered. We do this by writing tests that expect an output of false where the input and an output do have the same size, do contain the same elements, but the output isn't ordered. Like this. Both the input and output provided to isValid have the same 2 people, Ash and Cal, but the output isn't ordered. Having constructed these test suites, we can discover which properties students had the most trouble enforcing by counting the is-valids that were accepted by the functional suite but were rejected by each of the sub-property suites. Recall that 3 submissions weren't functional and 1 of the functional submissions was not relational. Only 4 submissions didn't enforce ordering. 34 didn't enforce that the input and outputs had the same elements. And 16 didn't enforce that the inputs and outputs had the same size. The uncertain ordering that makes this problem relational clearly was not the most difficult aspect of the problem for students. In our paper, we go even deeper, further decomposing enforce same elements into additional properties to discover whether it could be the case that students merely check whether the input is a subset of the output, but not vice versa. We also discuss 2 other case studies, a second PBT assignment in the Accelerated Intro course, and the PBT assignment in Logic for Systems. I encourage you to check out our paper for more details. For now, I'll leave you with 3 key takeaways. First, relational problems, which are common in computing education, can effectively motivate the teaching of PBT. Second, in lieu of sophisticated tools like Quick Check, we can provide students with a general scaffold for property-based testing. And finally, that we as educators can apply property-based thinking to evaluate students' property-based tests, to get property-based insights into their work and where they struggled. That concludes my presentation. Thank you for watching.